Welcome to the 6th lecture of module 5. In module 5, we are discussing distillation, and in our previous lecture, we have started with fractional distillation. And we have learned how to operate the fractional distillation and how to obtain operating lines for rectifying section and for stripping section. Today, we will continue with our lecture of fractional distillation. We will first discuss the equimolal overflow. Our distillation calculation to obtain the number of plates would be much easier if the operating line are straight lines. And this is true only when the liquid and the vapor flows among the rectifying sections and the stripping sections do not change, then this line, operating line for rectifying section and operating line for the stripping section should be straight line. So, what is then required? This flow in both the sections be constant, that is required equimolal overflow or constant molar overflow, which is required. And these conditions, the constant molar overflow happens when the molar heat of vaporizations of the liquid is essentially equal to the vapor. So, the quick way to check the validity of this assumption is to compare the heat of vaporizations of the components. If the heat of vaporizations of the components ratio is 1:1, roughly 1:1, then we say that the assumption is acceptable. So, when the flow is equimolal, in that case we can see that at x is equal to x d, y should be y d. So, the rectifying section line should pass the point x d and x d. It will be easy to plot the operating line with the slope of the operating line and the point x d and x d. Similarly, for stripping section, if we know the slope, the stripping section would start at the bottom composition of x w, and with the slope we can plot the operating line for the stripping section. Now, we will discuss feed tray. Let us examine the steady state material balance on the feed tray. Consider this is the feed tray, where the feed which is coming with a composition of ZF and liquid which is coming down below the feed tray is L bar, liquid which is coming from the top section is L, liquid which is going to the feed tray is G bar, and which is coming out from the feed tray is G. So, if we write the total material balance, F plus L plus G bar should be equal to L bar plus G. Now, we will write the energy balance. We know that in the energy balance, if we assume the change in enthalpy of a phase as it passes through the feed plate is negligible. So, if it is negligible, the change in enthalpy when the phase passes through the feed plate, then we can write the energy balance equation F H F plus L H L plus G H G is equal to L bar H L plus G H G. So, from this we can write L bar minus L into H L would be equal to G bar minus G H G plus F H F. Now, if we use the total material balance in these equations, we will get G bar minus G is equal to L bar minus L minus F. So, if we substitute, the energy balance equation would be L bar minus L into H L is equal to L bar minus L minus F H G plus F H F. So, if we just simplify, L bar minus L H L would be equal to L bar minus L H G plus F into H F minus H G. So, we can write L bar minus L into H L minus H G would be equal to F into H F minus H G. So, then we can write L bar minus L by F should be equal to H F minus H G divided by H L minus H G is equal to H G minus H F divided by H G minus H L, which we can say a quantity Q. Now, this L bar minus L, this is the increase in the liquid flow rate across the feed tray. So, across the feed tray due to introduction of feed. So, then this we can say the rate of input of liquid with the feed. So, we can write Q is equal to L bar minus L by F is the fraction of the liquid in the feet. Again we can write Q is equal to H g minus H f divided by H g minus H L, which we can write heat required to convert 1 mole feet to saturated vapor. Divided by molar heat of vaporization of saturated liquid. Now, it will be interesting to know the feed line, its location. So, where the rectifying section line and the stripping section line intersect, at what location. So, that is very important for the calculations of the number of plate in the fractional distillation. The point of intersection, which is x y, must be satisfied by the material balance equations of both rectifying and stripping section. Let us do the material balance equations both the sections as we have done before. G y is equal to L x plus d x d, and G bar y is equal to L bar x minus W x W. This is the rectifying section, material balance, and this is stripping section. Now, if we subtract the rectifying section equations from the stripping section equations, we will get G minus G bar into y would be equal to L minus L bar into x plus d x d plus W x W. Now, if we use the overall material balance equations, we would obtain G minus G dash into y would be equal to L minus L bar into x plus f. So, this part is f z f. If we divide the total material balance equations by f, and use definition of Q, then we would get G bar minus G by F plus 1 is equal to L bar minus L by F is equal to Q. and now if we take this relation, so it would be G bar minus G divided by F into Y is equal to L minus L bar by F into X plus Z F. So, if we use this relation, it will be minus Q minus 1 into Y is equal to minus Q x plus Z F. So, from this we will get Y is equal to Q by Q minus 1 x minus Z F by Q minus 1. So, this is another operating line in addition to the two operating lines we have obtained earlier for stripping section and the rectifying section. This is called the feed line or Q line. Now, it would be interesting to know the locations with this Q line or feed line equations. As we have discussed before, there are different kinds of feed conditions we can use. If we consider feed as a cold feed, then the slope we can see Q would be equal to L bar minus L by F. So, the slope would be positive and it will lie to the vertical line, since Q is greater than 1. Now, in case of saturated liquid, where Q would be 1. So, the operating line or Q line should be vertical. The third case where the feed is saturated vapor. So, in that case the Q would be L bar minus L by F, which is horizontal in nature, Q would be 0. So, the operating line or Q line would be horizontal. For a mixed vapor liquid feed, the slope would be negative, it is less than 0. Because of negative slope, it will be below the horizontal line. Now, if feed is mixture of vapor and liquid, in that case the slope is negative and the value of Q lie between 0 and 1. So, Q is greater than 0 and less than 1. So, it will lie between the vertical and the horizontal line. Now, if feed is superheated vapor, in that case value of Q is less than 0. So, the line will lie below the horizontal line. The rectifying section line and the stripping section line will pass through the intercept through the feed line. So, feed line should pass through the intersection points of the stripping section line operating lines and the operating line of the rectifying section. So, if the column has an intermediate feed or product, the same rule apply. Now, we will discuss the distillation calculation. So, there are assumptions we have done before, that is the equimolar overflow. If the equimolar overflow, as we discussed at the beginning, if that is applied, in that case the operating line of stripping section and the rectifying section is straight line, and in that case the graphical method of McCabe Thiele can be used to obtain the number of ideal plates required. Or if the equimolar overflow cannot be assumed, in that case we have to use the energy balance equations in conjunction with the material balance equations. So, the method which we follow is the Panchon and Savarit method. So, today we will discuss the McCabe Thiele method of analysis, how to determine the number of plates and the mole fractions in the liquid phase, and then the total reflux, the limiting cases we will discuss with an example. As we discussed before, this is the tray distillation column, where we have single feed and that condenser, and there is a reflux and only one product outlet and one overhead products and one bottom products. There is no other side card. So, we know the operating line equations. So, this is L bar by G, the slope G bar, and this is G W and G W. As we discussed before, the locations or the feed line or the Q line, how it will vary in different situations for different feed conditions. How to obtain the operating line we have discussed for both the sections. We will discuss how to obtain the number of theoretical stages required using graphical method and theoretical method. So, in case of graphical constructions for McCabe Thiele is generally used for the constant molar overflow. The procedure we follow: first plot the equilibrium curve and the 45-degree line diagonals, which is shown over here. We know the equilibrium data. So, the y, x and y we can plot. So, this is the equilibrium line, the blue line indicates the equilibrium line and 45-degree diagonal. Then we have to locate the feed conditions and the distillate overhead and the bottom conditions for the more volatile components, which are given x d, z f, the feed compositions, and x w, which is the bottom compositions of the more volatile components. So, these points are located and then this should be plotted. Calculate slope of q line q by q minus 1, this is the slope of the q line, and draw the q line using x is equal to z f, that is the feed conditions. So, at x is equal to z f, this is the q line. As soon as the q line is plotted, now we will calculate the y line intercept. So, how to calculate? We located the point at x d on the 45-degree diagonal, then we have to calculate x d by r plus 1, that is the rectifying section line, and draw the operating line for this section. So, we will see how to do that. We know this point, we know x d by r plus 1, x d is known to us, and the r is the recycle ratio or reflux ratio. So, if we know r and x d, we can calculate x d by r plus 1, we know this point, and then we can plot the operating line between these 2 points. Now, draw the operating line for stripping section using x w and the intersection between rectifying operating line and the q line. So, the q line and rectifying section line intersect at this point. This line is q line. So, it intersects at this point, and we know the bottom points x w. From this point and the intersection point, we can draw the operating line for the stripping section. So, we know both the sections operating line and the q line, and this is the intersection point, which is the feed plate locations. Now, we will calculate the number of plates required by graphical method. So, we will start at locations x d. We can start from any point, either from the bottom or at the top of the tower. So, if we start at x d, then from the x d locate x 1 and y 1 by drawing a horizontal to the equilibrium line for stage 1, and then find y 2 from the equilibrium line to the vertical line on the rectifying section operating line. So, we will plot from here to here horizontal line, and then we will plot the vertical line. So, this is for stage 1, and then the same procedure we will follow from y 2, draw another horizontal line to the equilibrium line and then vertical line. So, this should come here. So, this will give another stage, and the same procedure we will follow until we reach x w or x w which is less than z f. So, when x I less than x w, we will stop it. This is number 1, number 2, number 3, number 4. 4 plates are required in this case. Let us take an example. A mixture of 45 mole percent N-hexane and 55 mole percent N-heptane is subjected to continuous fractionation in a tray column at 1 atmosphere total pressure. The distillate contains 95% N-hexane and the residue contains 5% N-hexane. The feed is saturated liquid. A reflux ratio is 2.5 is used. The relative volatility of N-hexane in mixture is 2.36. Determine the number of ideal trays required. So, this is the similar problem as we discussed before. Given alpha values, alpha is equal to 2.36, and we know the relation between y is equal to alpha x divided by 1 plus alpha minus 1 into x. So, if we take different x values and we can obtain y values using this alpha is equal to 2.3. So, this is the table which shows the equilibrium data. So, we can plot the equilibrium curve. Now, the distillate contains which contains 95% N-hexane. So, that means x d is 0.95. We know the point x d, this point is 0.95, and feed has 45 mole percent N-hexane. So, xf this point should be 0.45, and then the residue is 5% N-hexane. So, x w this point is 0.05. And the reflux ratio R is given 1.5. So, we can calculate x d by R plus 1, which is 0.95 divided by 1.5 plus 1, which is equal to 0.38, and we know the slope of the Q line. So, this x d by R plus 1, this we know. So, we know this is x d by R plus 1, and this point is known, which is XD. Then with this point and with this point, operating line for the rectifying section we can plot. Similarly, we know XW 0.05, 0.05. So, before that the feed conditions which is given, the feed is saturated liquid. So, Q is equal to 1. So, slope of the Q line is equal to Q by Q minus 1 is equal to 1 by 1 minus 1, which is infinity. So, it will be a vertical line from this point at x f x f. So, this is the Q line. So, we know the Q line and we know the intersection point. So, using the XW values and intersection point, we can plot the stripping operating line. Then the similar procedure, we start at the top of the column at XD and we draw a horizontal line to the equilibrium curve and then to the operating line, then equilibrium curve and operating line. And if we do that, the number of ideal trays is 6. So, 6 number of trays are required. Now, there are two limiting cases in case of fractional distillations. One is the total reflux. This gives minimum number of ideal stages and second is the minimum reflux. So, this gives the infinite number of ideal stages. In case of distillation design, there is a normal trade off between this reflux and stages. What reflux ratio we should use and what number of stages we require, there is a standard optimization problem, for which we need to consider the cost parameter to obtain the optimum reflux ratio. Today, we will discuss the total reflux, where we will obtain the minimum number of stages. At total reflux, what happens? All the vapor which will be condensed at the overhead reflux drum will be liquid and returned back to the column without taking any product, without removing any product from the reflux drum. So, in that case, the distillate would be 0 and the reflux ratio, which is R L0 by D, would be infinity. So, no product is drawn from the reboiler either. So, all the liquid flowing to the reboiler is vaporized and fed back to the column. So, column which is operating at total reflux condition under steady state conditions, there should not be any flow of the feed into the column. So, we should not give any feed when the column will operate at total reflux. So, at total reflux, the slope of the operating line OL R by R plus 1 is unity and it passes through the XD point and fall on the diagonal line. So, the operating line of the rectifying section coincides with the diagonal. Similarly, the operating line of the stripping sections also coincides with the diagonal. So, these situations at total reflux, it gives the minimum number of theoretical stages required to achieve a given separation. This total reflux is very common during the startup of the column till steady state condition is reached. At the startup and the product is withdrawn until a separation close to the desired is achieved, and after this we will continue feed flow to the column. So, we will see graphically how to obtain the minimum number of stages when there are total reflux in the column. So, at this stage at total reflux, so both the operating line will lie on the, so this is operating line for the rectifying section and this is the operating line for the stripping section. So, this will coincide. So, we can obtain, we know x d and we will make the stage of operations as we did before. So, it will give the minimum number of stages required for the operation. So, this is the graphical analysis. Now, there is another method which is known as the Fenske equations, which is a shortcut method. Fenske equation, which is a shortcut method to obtain the minimum number of stages. So, there are so many approximate methods are available, it is one of them to obtain the minimum number of stages. Let n m be the minimum number of stages excluding total reboiler. Now, alpha w is the relative volatility of A at reboiler temperature and pressure. Now, x w and y w, these are the equilibrium composition of liquid and vapor in the reboiler. Then we can write y w divided by 1 minus y w would be equal to alpha w x w by 1 minus x w. Now, the vapor which is leaving the reboiler and entering the lowest tray, that is N m, has a mole fraction of y w, and the liquid which is leaving N m it has x n m. So, the point x n m and y w, this lie on the operating line. At total reflux, operating line coincides with diagonal. So, x n m should be y w. So, if we put in that equations, it should be x n m by 1 minus x n m would be equal to alpha w x w divided by 1 minus x w. Applying the same procedure, we will obtain y n m divided by 1 minus y n m would be equal to alpha n m x n m divided by 1 minus x n m. So, if we apply for tray n m. So, we can write alpha n m into alpha w into x w divided by 1 minus x w. Similarly, if we apply same thing in case of n m minus 1, we would be obtained y n m minus 1 divided by 1 minus y n m minus 1 is equal to alpha x n m minus 1 divided by alpha, this will be n m minus 1 divided by 1 minus x n m is equal to alpha n m minus 1 into alpha n m alpha w into x w divided by 1 minus x w. So, the point x n m minus 1 and y n m, this point lie on the operating line. And coincides with diagonal. Therefore, in this case we can write x n m minus 1 would be y n m. So, if you continue same procedure for the top tray, y 1 is equal to x d. If we include that, we can write x d by 1 minus x d would be equal to y 1 divided by 1 minus y 1 would be equal to alpha 1, alpha 2 and so on alpha n m into alpha w x w divided by 1 minus x w. So, from this we can write x d by 1 minus x d is equal to alpha average to the power n m plus 1 into x w by 1 minus x w. So, from this we can write n m plus 1 should be equal to log of x d into 1 minus x w divided by x w into 1 minus x d divided by log alpha average. Let us take a very simple examples, same examples which we have discussed before. A mixture of 45 mole percent n-hexane and 55 mole percent n-heptane, which is subjected to the fractionation at 1 atmosphere pressure. The distillate contains 95% n-hexane, residue contains 5% n-hexane. The feed is saturated liquid. The reflux ratio of 2.5 is used. The average relative volatility is 2.36. Determine the number of ideal trays using Fenske equations. So, the data which is given, that is x d is 0.95, x f 0.45, x w 0.05, alpha average is 2.36 and we know N m plus 1 is equal to log of x d into 1 minus x w divided by x w 1 minus x d divided by log of alpha average. So, if we put the values, it is log of 0.95 into 1 minus 0.05 divided by 0.05 into 1 minus 0.95 divided by log of 2.36. So, this will give around 6.8. So, from here we can calculate N m is equal to 6.8 minus 1, which is equal to 5.8. Almost same values we have obtained using the graphical method. Thank you.